Okay, should be recording now. And yeah, so hello, welcome to the 6th recitation for this section. And let's get started. Programming assignment 3 is out now, so you guys should definitely get started on that. And you guys could attend office hours and stuff to ask questions if you get started early. And yeah, the graders this time are Prince and Azita. So if you have any questions about your grades once they're done grading for PA2, you guys should contact them. Their emails should be on the pages and on Canvas. So today we're going to be going over data representation, number system conversion. So like going from binary to decimal and then to hexadecimal. And we have floating points in binary and how we represent those. And then we have just a quick, we'll just talk about assembly real quick, because I think you guys are starting to dive into that now. So yeah, first up, we have data representation. And so this is from the last recitation, the slide, just to kind of rejuvenate your memory. So we have binary, it's base 2, zeros and ones. And yeah, so you guys should be pretty familiar with this now. And then we have hexadecimal, and it's 0 through 9, A through F to represent the values. And yeah, so when we write hexadecimal numbers, we use this 0x to represent that it's a hexadecimal. And then everything after that is the actual hex number. And then we have conversion, so how to convert between these. So this is how to convert from hexadecimal to binary. And so it's pretty simple. You basically just take each element of your hexadecimal number and you get its binary equivalent. So the binary equivalent for 3 is this 0011. And then you do the same thing for all of them. And then you simply just replace each element with the binary equivalent. So in place of the 2, you just write the 0010. And then like in place of the A here, we just write the 1010 that we calculated was its hex or binary equivalent. And yeah, that's basically how you convert them. And if you have like bigger values, I guess you could just use a hex to binary chart to quickly determine them. But like it's only going to be up to 16 or F. And so it should or 15, I guess. And then, so it shouldn't be too bad to convert it to the binary version of it. And then we have binary to hexadecimal, so the other way around. So it's a similar concept. You basically, so here we just took each of the elements and got its binary equivalent. And here we do the same thing, except we group them into elements of 4 digits. So blocks of 4 digits or less, like if it doesn't divide evenly by 4, whatever amount you have left at the end. So you group them into blocks of 4 digits, and then you just replace each block with its hexadecimal equivalent, because we know that a hexadecimal element can be represented by, or a 4-bit binary string can be represented by 1 hexadecimal digit. So yeah, that's basically it. You just replace these, and that creates your hexadecimal number. And as we said, it's a lot. You could represent hexadecimal numbers or long binary strings with a lot less using hexadecimal numbers, because 4 bits correspond to one character, and it just compresses the number a lot. And yeah, so next we have decimal to binary. So basically what we have here, this is like the first slide of the 2 for going from decimal to binary. So So each value in a decimal number has a place value. And as we could see here, this is the ones place or the units place. And then we have the tens, hundreds, thousands, and then the nths place. Or yeah, and then same thing with binary. So you have the twos, the fours, the eights,
10,
and
22.
yeah. And then so basically you just based on that concept, this kind of method is derived to convert decimal numbers to binary numbers. So you write down the decimal number. So let's say we want to convert the number 29. So you write it down, you divide the number by 2, and you write the result underneath. You basically just write everything except for, like, you don't write the decimal part, the part after the decimal point. And so it's only the whole number part. And then you write the result underneath, and you write the remainder on the right hand side, which is what's written here. And so this is going to be either 0 or 1 after you divide it by 2, because that's just like, if it's an odd number, you divide it by 2, the remainder is 1. If it's even, divided by 2, the remainder is 0. And then you just kind of keep doing this over and over. Just keep dividing it by 2, writing the remainder on the right. And then the most significant bit is going to be at the bottom. The least significant is going to be at the top. And so you just write the number starting from the bottom up. And so this 29 becomes 11101 in binary, which is exactly what we have here. And yeah, so this is kind of the hardest conversion out of the 3 that we did, because this is pretty simple. This is pretty simple. And then here, it's just kind of this algorithm, which is also, it's not bad. And then, so basically, these are kind of the only 3 conversions that you need to know to convert between these 3 values, because the binary serves as mediator. So you don't actually need to know how to convert from decimal to hex or hex to decimal, because those are more complex algorithms. And I mean, there are algorithms out there for that, of course, but it's just a lot easier to do it this way, because algorithms to convert between binary and a number, and binary and hex and binary and decimal is a lot easier. So if you want to go from hex to decimal, you just take the hex, convert it to binary, convert it to decimal. And if you want to go from decimal to hex, you just do it the other way around. And so binary makes the conversion easier instead of memorizing another algorithm, which is more complicated. And then we'll talk about fixed and floating points. So wait, did you guys have any questions about any of the conversions that we did here? Or how you'd get from hexadecimal to decimal or backwards? um, so you're asking why this method works the way that it does. So I guess division by 2 is kind of equivalent to bit shifting a number left 1. And I guess when you take the remainder of it, that actually gets you the bit of the number. So once you guys do work more with bit shifting, you'll start to see how that works. So yeah, when you bit shift a number left by 1, that's equivalent to dividing by 2. And bit shifting it left by 1 just brings the next bit over. And so using that method, by dividing it by 2, you're kind of bit shifting it left, and you keep getting each consecutive bit by taking the remainder, and then that becomes the complete binary number. Yep. Okay, so yeah, I guess we could move on to fixed and floating points. So basically, we went over this part last time. And so in decimal numbers, each number to the right of the decimal point has a value of 1 over 10 to the I for each digit in the ith place. So um, how we have the hundredths and the tenths and the thousandths place, it's basically 1 over 10 to the negative 1 and 1 over, or yeah, so after the decimal, it's 1 over 10, 10 to the 1 and 1 over 10 to the 2, or 10 to the negative 1 and 10 to the negative 2. Yeah, so you could do the same thing in binary, and this is the concept that we use to convert to convert floating points between binary and decimal. So here's an example of just how decimal numbers work. So if you have the number 8.625, this is the place value that each of these numbers takes, and you just multiply each number, each actual digit by its place value, and sum them all up, all of those products, and that gets you the actual number. So that's how the decimal number system is formatted. And so by using that same methodology, we can do that to binary numbers, where the base, instead of being 10, which it was here, gets replaced by 2. So now when we do want to convert this binary fixed point number over to decimal, we just kind of do the same thing. So we take each digit, multiply it by its place value, take all the products, add them up, and we get the final number 8.625, which is what the example I had here. 8.625 is 1000.101 in binary. And so that's how you convert a binary fixed point number to a decimal fixed point number. And so because we just did binary to decimal, but what if we want to go from decimal to binary, right? So in order to do this, we have an algorithm here, and this algorithm basically allows us to convert the numbers. So just give me 1 second. Okay, yeah. So basically, let's say we have a decimal fraction, and we take that decimal fraction, and while it's greater than 0, we multiply it by 2. And if that number is greater than or equal to 1, we output a 1, and we subtract 1 from the number. Otherwise, we output a 0. And basically, if you follow this algorithm, you will be able to convert the decimal number into a binary number. So I actually wrote up a little script that'll allow us to see this happen, and I'll just pull that up and run it. Just give me 1 second. Let me unshare this and share the other one. Mm, Give me one sec. Okay, yeah. So let me share this quick. Okay, so you guys should be able to see my VS Code screen here now. And so I basically have that same algorithm here. And so I have one function, decimal to binary, where so if we just enter a decimal a decimal string, it'll output the binary equivalent of that. So when I run that, it tells me that 0.625 is equivalent to 0.101 in binary. And I have another function that actually displays the information as it runs. So basically, when it's converting it, um, we can we can see the algorithm here. So the number is initially 0.625. It multiplies it by 2 because it's greater than 0. It multiplies it by 2. It becomes 1.25. So it outputs a 1, which is what we see here. And then the number is point, and then yes, the number we subtract 1 from it. So the 1.25 becomes 0.25. Multiply that by 2, that becomes 0.5, and that number is still greater than 0. So we output or that number is no longer greater than or equal to 1. So we output a 0. And so that's the 0 we see here. And then finally, we take the 0.5 and and yeah, and then we multiply by 2 and we get 1, and then we multiply, and then we go back into this if statement and we output a 1, and then the number um, the number is no longer greater than 0 because the 1 minus 1 makes it 0. So the while loop ends and you get your final string, which is 0.101. Oh yeah, sorry. It's written in Python, and I just thought that would be a lot easier than writing it in C just for the purposes of this demonstration, because this was the main thing that I wanted you guys to see. And um, yeah, so let me share the slides again. Yeah, so that's the algorithm, and that's how you convert um, decimal fixed point strings to binary. And so there's actually a problem here. So when we convert the decimal 0.1, which is written in base 10, to binary, the answer is this. It's 0.000 1100 over and over again. And so it becomes an infinite repeating string. And if I ran that algorithm on 0.1, it would return the infinite repeating string. And so this is kind of a problem because we can't just if we need to represent a simple thing like 0.1, we can't just store an infinitely repeating string in our memory. So um, so then we need to find a way of representing floating points with a fixed number of characters. So first, let's talk about scientific notation before we jump into the way of representing the floating points. So um, we all know scientific notation. It's basically um, taking the number uh, and getting the base to be between 0 and 1, and then we just multiply by a power of 10 in order to shift the decimal point over. And so we could do the same thing with binary numbers. So this binary number 100 becomes 1 times 2 to the 2. And the decimal point that was here gets shifted over here in front of the 1. And so you could also write binary numbers in scientific notation with base 2 instead of base 10. And So this gives us a natural way of thinking about floating point numbers. And so the floating point number 0.25 in base 10 um, equals, um, wait, okay, yeah. So this was, even happened? Okay, basically this number is 1 times 2 to the negative 2 in binary. I think I messed up the slides there. But yeah, so basically when we convert this number over to its binary equivalent, it becomes 0b1 times 2 to the negative 2. And so we could create a standard to represent floating point numbers based on this idea of storing it based on the exponent and uh, what's the exponent and the sign of the number and the part after the decimal point. So, so we have this standard in order to do that. It's called the IEEE 754 standard. And it's called that because it was established by this institute here. And so it just allows us to compute floating point numbers and represent them. And so they offer 3 different precision levels: single precision, which is 32 bits; double precision uses 64 bits to store the floating point number; and extended precision uses 80 bits to store that number. And then, so there's 3 basic components to this. There's the sign, the exponent, and the mantissa. So what the sign is, it's just 1 bit, which represents if it's a positive or negative number. If it's 0, it'll be a positive number. If it's 1, it'll be a negative number. And the exponent represents what the exponent is going to be on the number when it's written in scientific notation. And the mantissa is just the part after the decimal point. And so that's represented here. And so with 32 bits, 1 bit is assigned to the sign, and actually 1 bit is assigned to the sign in either case because it's either positive or negative. And then 8 bits are assigned to the exponent, and 23 bits are assigned to the mantissa. And so if we go forward, we have, okay, so let's talk about single precision. So we have yeah, so we just talked about this, the 1 bit for sign, 8 for exponents, 8 for the exponent, and 23 for the mantissa. And 0 is positive, 1 is negative. And this is a type float, is what, like whenever you have a type float in a language, that's a single precision number represented using this way. And when we actually have a type double, it's a double precision number because so it gives 11 bits to the exponent and it gives 52 bits to the mantissa, which is the part after the decimal point. And so this actually gives you a lot more precision. And this is what a type double is. And so the range for wait 1 sec. Actually, I think I had an issue here with the range, but yeah, I'll fix that when I upload the slides. But yeah, basically the range of double precision is larger than the range of single precision is the point I was trying to make by putting the ranges here. And yeah, so so now you're probably asking, how do we actually store these how do we actually find out what these numbers, what these fields are? So we have the sign field. Well, that's pretty self-explanatory, but then we have the exponent field and the mantissa field. And so how do we actually get what those are? So basically we have normalized values. So there's 2 ways of doing this. One is normalized and the other is denormalized. And so for the normalized way, we we define some rules. So basically the exponent field here cannot be 0 or all ones. So basically all zeros and all ones. And so the exponent here is actually the binary value of the exponent minus the bias. So when we have the exponent of the number, we don't actually just convert that straight up to binary and store those bits here or here. What we actually do is take that number, subtract the bias from it, and store that, because we need to be able to store both positive and negative exponent values. And in order to do that, we need so the binary number would only allow us um, to store the positive numbers. So what we do is we subtract the bias from it, which is represented by this formula based on the number of bits we're using. So if we're using 8 bits, which is what we do with single precision, we give it we set the bias to be the number 127, and so that allows our exponents to be in the range negative 126 and 127, rather than the 0 to 254 that you'd have if we didn't use the bias. So yeah, so now that we have the exponent, this is how we calculate the exponent and the mantissa. So in normalized form, we assume that it's going to begin with a 1, and and then after the decimal point is the mantissa field that we actually store, which is this or this. And so that's going to be 23 bits after the 1. And so an example of this would be if the sign is 0, the exponent is 1, and the mantissa is 1. We get this value here because since the sign is 0, it's a positive number. The mantissa is 1, so we just put a 1 here after the decimal point. And then the exponent is 1, so we take the 1, subtract 127 from it. That gives us negative 126, and that becomes our exponent. So let's do some practice with this. So let's say you're given this number where the sign is 0. This is the exponent. Oh wait, what did I do here? Sorry, just give me a second. Okay. Okay, actually, let's just go on to the next example because I think I actually left this one unfinished for some reason. Okay, so let's say we want to find, let's say we have the number 5.625 in base 10, and we want to find the IEEE standard to store this. So what we do is first we convert the 5.625 into its binary form, and once we do that, we move the decimal point over 2 places, and because we want to, so the 1 is assumed, and then everything after the 1 is actually the mantissa, and the 1 is assumed because any number that starts with the value greater than 1 will have a 1 at the end here, because there won't be extra, I mean, if there are extra zeros, they don't really mean anything. And so the last 1 value is what that'll always be there as long as the number doesn't start with 0. So we assume the 1, we move the decimal point over 2 places, and then because we moved it over 2 places, we set the exponent to 2 here. And then, so because the exponent is 2, we add 127 to it to store the binary equivalent of it, and we get the number 129, and that number is equivalent to this binary string here in binary. And yeah, so to find the converted value that we want to set the exponent to, we add 127, and then to find the unbiased value, which is the actual stored value, we subtract 127. But yeah, so we have to account for the bias, so we add 127 to it, and we get 129. We convert that to binary, and then the mantissa here is everything after the decimal point. So the mantissa is 01101, and the sign bit here is a 0 because, as we can see, it is a positive number. And so that's basically all we need to get the final version. So we just take the 0, we put it here as the first bit. We take the exponent that we calculated, the biased version of it, and we put it here as the exponent field. And then we just take whatever we have in the mantissa and we throw it over here. And then we just fill in the rest of the bits here with zeros because the mantissa is only 5 bits long, and we start from the left. So we do the 01101, and then the rest of it gets filled in with zeros. And that's it. So this is your final answer. And if you wanna check it, you could just convert backwards. And in order to do that, you can. So we get the plus. So let's try to convert this backwards. So we have the plus sign because it's a 0, and we have the 1 because 1 is assumed in the normalized form, which means it starts with a number greater than 0, so it has to be, or yeah, the number to the left of the decimal point is greater than 0, so it has to start with a 1. And then we have our mantissa, which we get from here, and we don't need to write the rest of the bits. And you multiply that by 2 to the so we take whatever this is, convert it back to decimal, 129, and then we subtract 127 from it to get the actual stored value, and that's how we get the 2 back here. And then we could see that this is the binary equivalent that we converted. So the 101 is 5, this one is 1/2, this one is 1/8. Add them all together, you get 5.625, which is the original value that we started off with. So we could see that this is how you convert the 5.625 decimal into the IEEE standard to represent floating points, and then this is how you can convert it back based on what you know. And then after that, we also have denormalized values, which is basically, so what we talked about here is we assume that the first digit of the number is going to be a 1 when we store it, as in, and that'll happen whenever anything to the left of the decimal point is greater than 1. But how do we store a number that's like 0.12 something or 0 point anything? We can't assume that the thing over here is a 1. So when we convert it back, we have to make sure to convey that information that it doesn't start with a 1. And in order to do that, we used denormalized values. So this is how you represent a number where the leading digit is not 0. And so this is where the exponent, so in this case, we have some rules as well, just as we had rules in the normalized values. And so the rules here are that the exponent field is always set to 0 in this case. And that's how we know that we're dealing with a denormalized value. And then the exponent will always be 1 minus the bias. So which is negative 126 for float, and that'll always remain the same. And then we have the mantissa, which is just the mantissa field, and we have to remember that there's no leading one, and so it starts. So if we have something like this, mm, yeah. So I guess we'll just go over. I mean, yeah. So basically, when we have something like this, sine 0, exponent 0, and mantissa 1, 0, um, this is what it comes out to be. And yeah, so that's basically so if we actually multiply out by the 2 to the negative 126, this decimal point will move over 126 places, and this is a number that starts with a 0. So that's how we store numbers that start with zeros on the left side of the decimal point. And so if you understand denormalized values, it's the same procedure to get the normalized version. And so this example applies to that as well. You just have to remember to not assume the leading 0 or the leading 1. And then, so yeah, this is why we need to have denormalized values. So, so basically there's a number here, which is the minimum normalized value. And there's a number here, which is the maximum normalized value in the negative part. But there's also numbers in between these two values that we have to represent in computers. And we can't do that using the normalized way. So that's why we need to use the denormalized way to represent those numbers. And so that's the reason that we have that. And then we also have our special cases. So we also need to represent 3 other things, which is positive infinity, negative infinity, and nan or nan, which stands for not a number. So when we store positive infinity, basically the exponents in the infinities are set to all ones. The mantissa is set to all zeros, and then the sign determines whether it's positive or negative. So 0 means positive, and the 1 means negative. And so that's how you represent negative and positive infinity in computers. And then we also have not a number. And that's used to represent the results of invalid operations. So if you do something like 0 divided by 0, you need to output something that you just need to output something that's actually incorrect. That actually tells the user that you did that they did something incorrect. And so nan can represent that that value. And so for nan, the sign could be anything. The exponents have to be all ones, and the mantissa can be anything. And basically, if you have something in this form, the computer will know that it's not a number or positive or negative infinity. Yeah, and in this case, it has to be anything other than all zeros, because if it is all zeros, then it'll be confused whether it's positive infinity, negative infinity, or nan. But yeah, so this has to be anything other than all zeros. And then, so you guys have started talking about assembly, right? I think in the past lecture. And so let's just like quickly look at what assembly is. And so basically, whenever we have a file such as p1.c, it goes through these 4 stages. So we start off with the C program, which is just a text file, and then the assembly program, which is the text file, and then we have the compiled binary, and then we have the executable binary. And so what we'll be talking about at this point in the course is this stage, the assembly stage, and how basically assembly syntax and how it works and what it is. And so basically assembly is just this bullet basically represents the essence of what assembly is. And it's just a strong correspondence between the instructions in the language and the architecture's machine code instructions. So when we have a language like C or Java or Python, um, we what we write doesn't actually translate directly into what the computer is doing, right? It's a much more high level view, such as a for loop or an if statement or something like that. So when we do assembly, you guys will get to see what the computer is actually doing under the hood, and how things are moving around in memory in order, and like how information is being exchanged between the computer's architecture, like between the memory and the CPU registers, and how all of these things like for loops and if statements and declaring variables and getting variables and how all of that's actually happening. So yeah, basically anything. So in assembly, when we write things, it'll be like move X to Y, or like from this register to this register, and then it'll just basically be instructions like that, which are going to be very simple, straightforward instructions that are created based on the program that we write. So when we write a program in C, it goes through this assembly stage where the assembler generates these different commands for how these programs um, for exactly what your program does based on how it actually interacts with the architecture. And so there's a strong correspondence there between what's actually happening in the computer and what's written in the language. And so yeah, in assembly language, um, it's very straightforward instructions for what's happening in the computer rather than what you'd see in a high level language. And then we have, and then I just wanted to talk a little bit about the architecture that assembly deals with. And these things are important for you guys to know when you get started with assembly. So we basically at the highest, at this level, we have the memory and the CPU, and they each have their own components. So we have in the CPU, we have the program counter, the registers, the condition codes, and then in memory, you have all this data and you have the stack and the heap. And so basically instructions and data are exchanged between the CPU and memory. And assembly writes exactly how this data is being exchanged very explicitly. So like you'll actually write that a number is going, or a value is going from register A to register B. They're not called A and B. They're called, they have different names, but that's basically the essence of it. And you're going to write like, so flags are going to be set. So if you're comparing a value such as if A is greater than B, you're going to set a condition code or a flag to that'll be set to 0 or 1 based on the output of your comparison. And then you'll have to check that flag to see if it's true or false, and then continue based on that. So this is the architecture that we deal with when we work in assembly. And yeah, so it would be useful for you guys to get familiar with this. And yeah, so right now PA3 is out. Definitely get started on that, and come to recitation, come to office hours. Yeah, in office hours you could ask questions about that, and also on the piazza. And yeah, so you guys will be doing a lot of bit shifting, bit masking, things like that. And yeah, so you'll basically use those to do things that you would do in a different way before. You wouldn't really think to do bit shifting, but yeah, so you guys will learn how to do things using those methods. And what else? yeah, I guess that's about it for today. And um, yeah, that's all I had planned. And yeah, so you guys could leave if you need to go. And yeah, I'll stop the recording now. Yeah, no problem.